Assalamualaikum. My name is Muhammad Zikri bin Muhammad Nazri. I am the leader of Group Techno. Now I'm going to introduce our team. As you can see, my name is the first one, Muhammad Zikri bin Muhammad Nazri. Second one, Lokman Hakim bin Rashidi. Third, Muhammad Haikal Hafiz bin Muhammad Nazri. Nick Muhammad Fidaus bin Zainal Abidin. Muhammad Nurazin bin Azman. And Adam Haris bin Rosli. For our objective, to ensure a structured implementation process, this collaborative project established clear, targeted milestones. The core objectives include the first one, to design and implement a fully operational Java program capable of executing five separate algorithmic design paradigms, specifically greedy, divide and conquer, dynamic programming, backtracking, and sorting and searching, to resolve a centralized traveling salesman problem. The second one, to mathematically analyze and verify the absolute minimum traversal cost and path sequence derived from explicitly assigned 4-city symmetric distance metrics. For the last one, to critically compare the runtime behavior, memory overheads, and design trade-off of exact solution versus approximation approach.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haikal Hafiz. Today, I will explain about the greedy algorithm used to solve the traveling salesman problem. For this problem, we are given four cities which are A, B, C, and D, and the distance between the city are stored in a distance matrix. The main idea of the greedy algorithm is to always choose the nearest unvisited city from the current city because it makes the best immediate decision at every step in order to construct a complete route. The algorithm starts from city A. A Boolean array called visited is used to keep track of cities that have already been visited so that the algorithm does not repeat any city. The variable path and total cost are used to store the route and total distance. At each step, the algorithm checks all unvisited city and find the city with the shortest distance from the current city. This is done using a loop where the algorithm compare all of available distance and select the minimum value. Inside the loop, the algorithm check all unvisited city and find the shortest city with distance the current city. A condition is used to ensure that only cities that have not been visited are considered. The process is performed in condition where the algorithm always select the nearest available city, which represent the greedy part of the algorithm because it make the locally optimal choice at each step. So, using our distance metric, the algorithm move from city A to city B because the distance is 10 km, which is the smallest. Then, from city B, it moves to city D with a distance of 25 km. After that, from city D, it moves to city C with a distance of 30 km. The process is repeated until all of the cities are visited. After every city have been visited, the algorithm returns from the last city back to city A to complete the tour. The final route produced is A to B to D to C and lastly A with a total cost of 18 km. This problem is known as the traveling salesman problem where the salesman must visit every city exactly once and return to the starting city while minimizing the total distance. The grid algorithm solve this by always choosing the nearest unvisited city from the current city, and this process is repeated until all cities are visited. Thank you.
Okay, now I'm gonna explain about divide and conquer. For the first image, Java TSP divide and conquer. This block of code find the shortest route for a delivery person to visit four cities A, B, C, and D. Okay, next image, recursive helper method for TSP in divide and conquer. The first step is divide. It will split into sub-problems. Instead of calculating all four cities at once, the code divides the problem based on your next immediate choice. The code is the four loops. Uh, scans all available remaining series. The logic is it breaks the brick problem into smaller questions, such as what is the best route if I choose city B next? Or what if I choose city C? For the next step, conquer. Solve recursively. The code solves these smaller, divided subproblems by calling itself recursively until it hits a base case. The code for conquer, the recursive call on divide and conquer helper pushes the downsize problem further down the stack. The base case, the all visited, checks if all cities are conquered. If true, it returns a simple concrete value, the distance back to city A. The last step is combine or merge. It will select the best result. As the recursive call finish, the algorithm must merge the subproblems answer back together to choose the absolute best path. For the code, step 3, the merge step happens on math.min. It happens here. The logic is it takes the cost of your current step, this post next, and combine it with the solve downstream cost from next. It then select the minimum value to pass back up the change. That's all. Thank you. I will now pass to my friend.
For my section, I will explain the dynamic programming approach used in our traveling salesman problem. Dynamic programming is an optimization technique that solves complex problems by dividing them into smaller subproblems. Instead of recalculating the same routes repeatedly, the algorithm stores previously solved results and reuse them later. This slide shows the main dynamic programming method called dynamic programming TSP. First, the program creates a variable called visited all. Next, the program initializes two important arrays. The memo array stores the minimum cost for each state, while the path array stores the best route sequence. All memo values are initially set to -1 to indicate that the states have not been calculated yet. The program then starts the recursive process by calling dynamic programming TSP helper with position 0, which represents CTA and mask 1, which means only CTA has been visited. This slide shows the recursive helper method which acts as the main engine of the dynamic programming algorithm. The first condition is the base case. When mass equal visited all, it means all cities have already been visited, so the algorithm returns the distance back to CTA. Next, the program checks the memo table. If the state has already been calculated before, the store result is returned immediately to avoid repeated computation. The recursive loop then explores every possible unvisited city. For each possible route, the algorithm calculates the current travel distance plus the future minimum cost returned by recursion. The program continuously compares all possible routes and stores the smallest value. Finally, after all recursive evaluations are completed, the algorithm successfully produces the optimal path from CTA to B to D to C and back to CTA with the minimum total travel cost of 80.
I will explain how the traveling salesman problem can be solved using backtracking. What concept for backtracking? Backtracking is a sales algorithm that explores all possible routes but prompts unpromising one early. In TSP, it generates city tours, calculate travel costs, and discard routes that are more expensive than the current best solution. This guarantees the optimal path toward computation grow with more cities. In my coding structure, first, I define a define a distance metric to store the distance between city and an array for city names. Then I set array for then I set global variable. For example, min cost being as infinity and best part is empty. The function backtracking TSP initialize the route from city A and call the recursive function TSP backtracking. This function is the core. It trusts all unvisited city. Next, calculate the cost and last backtrack after each attempt. When all cities are visited, it adds the cost of returning to A and compare with the minimum cost. Finally, the main method print the base route and its cost. For example output is traveling salesman problem backtracking pick A to B to D to C to A. The cost is 18. The conclusion for backtracking is backtracking systematically explore all route, pronounce expensive ones, and ensure the best solution is found.
Now I'm going to explain my coding structure for insertion sort. Looking at the code, we define a method called insertion sort. It first print the initial array to the terminal and capture the length of the array to control our iteration. After that, the algorithm begins. It works at index 1. We assume the very first element is already sorted. The outer loop select each following element one by one. We call this the key and determine its proper place in the sorted portion of the list. Next, the call logic reside in this while loop. It compare our key with element on its left. If it find a larger value, it shift the value to the right to create a gap. Once the correct spot is found, we drop the key in. We also print each step to the console to provide clear traceability for our report. As in our sample output, the array slowly become ordered step by step. Insertion sort is highly efficient for small matrices like our 4-city TSP, and it is an in-place algorithm, meaning it uses very little memory.
Next, it is a binary search. For this part, we have to identify and sort the data set. Based on the coding, we have two variables. It is int low and high. Low at index 0 and high at the end of the array. Inside our while loop, we calculate the middle index. From loop, we have three-way condition. First, if the value at mid equals our target, we have found it and exit yearly. Second, if our middle value is less than the target, we know our target sits in the upper half. So we shift our low pointer to mid plus 1. Otherwise, if the middle value is too large, we shift our high pointer to mid minus 1 to search the lower half.